Thank you very much, Susan. It's nice to be here at TMLS. So since the introduction's already been done, we can jump right into it. I'll start with some review of the concepts of fairness and privacy and how they apply to ML on their own, and then we'll consider the combination of these ideas together and see what happens. So, as someone who works at a bank, I know firsthand the challenges that come along with trying to develop and deploy machine learning in such a highly regulated industry. When we build models, we need to think about things like reproducibility, stability, robustness, explainability, all these topics, of course. But two really stand out as being particularly important in highly regulated industries, which of course are privacy and fairness. Now, if you look at any given bank, any large financial institution, you'll find that they all have at least a team or even teams that are dedicated to these specific areas. And what's interesting to note is that these teams are usually completely separate entities. Now, on their own, both privacy and fairness are very, very rich areas of study. I say that genuinely because each of these areas have many different perspectives which are totally valid. You can think about them in many different ways. And I would go as far as to say there's no universal frameworks that work for every problem, and there's rarely correct answers in this space. But most discussions you see on these two topics choose either one or the other. Some very interesting things happen, though, when we start thinking about them together in their intersection. So the main takeaway of the talk, which I hope to explain more fully, is that applying very common, very standard privacy-enhancing technologies often makes unfairness worse. So let's go through these topics to lay some groundwork and then see how they work together. So let's start with fairness. The experts in the audience will know that there's many different ways to define fairness, which can be mathematically rigorous. And in a given scenario, one or the other of these definitions can be reasonable and the one you want to use. You really have to think about it on a case-by-case basis. What's also very interesting about this, though, is that several of these definitions are mutually incompatible. The first two that I've listed there, demographic parity and equal odds, usually, in most cases, it will be impossible, like literally impossible to satisfy both of these definitions at the same time. So usually, in fairness, we have to choose one and stick with it for a given problem. So I'll choose one here that we can keep in our minds to think about, which is performance parity or accuracy parity. But let's say you have a model and you've chosen to evaluate this model using a particular performance metric, then performance parity says across all groups, protected groups that you care about, the accuracy or the performance of your model should be consistent, should be the same. So let's say you work in the healthcare space and you're building a model to do cancer prediction. It's a binary classification task on some interesting histopathology images. Well, once you've trained your model, you might evaluate it across different gender groups, male, female, non-binary. You should find that the accuracy of your classifier is relatively the same across all these groups. Simple enough. Well, it's not so simple because within our data sets, we'll often find that some groups are minorities. And so these are harder to learn. We all know that machine learning, the performance of machine learning scales with the amount of data we have. So it's usually more difficult to learn minority groups and perform as well on them. But it's not all about the relative sizes of data. It's also about the complexity. Some groups end up being more challenging to learn for some inherent reasons. So there are solutions that you can try to do to improve the fairness of your models. If you have imbalance, you might choose to repeat a minority group more often using oversampling or a similar technique. You could also change the way you're training your model by, let's say, modifying the loss function and getting it to pay more attention to group labels of your data set. Or you could just train your model in any way you like and then look at the outputs and judge if your model's fair based on the outputs. If it's not, you can adjust those outputs to make it more equitable. You'll notice that all three of these solutions require us to know what the group labels are so that we can act on that information. But this itself is a problem because group labels are often sensitive information in and of themselves. In fact, in many cases, will be prohibited, at least in regulated industries, from collecting this information or using it in various ways. So this brings us, I think I hit the wrong button. This brings us to the next topic, which is privacy. As you look around the privacy landscape in Canada today, all through the legislation we have and the regulations we have for certain industries, overwhelmingly the focus is on protecting personally identifiable information. And the main way to do this is through anonymizing data sets. I don't really like this anonymization paradigm. It tends to think of privacy as a binary concept. If you have a data set with PII, it's either private or it's not. You've either removed the PII or you have not. But behind this anonymization paradigm, there's an assumption that data exists in a vacuum. So take this data set I'm showing here. Imagine that you have this data set in your work and it has some PII in it, like the name. You've decided that you will anonymize this data set by removing the names before releasing it. The problem is, as soon as you release your data, it no longer exists in a vacuum. There's many other sources of data out there in the world, and your friend might have been working on a similar project at a different institution, but they chose to anonymize their data set in a different way. They chose to remove the age information. And by eye even, you can link together these two data sets and effectively re-identify all the individuals in it, or de-anonymize the data set. In fact, there's very well-known examples of this being done in practice on publicly released data sets. But at least I think we can all agree that privacy should be about protecting the information of individuals within a data set. As data analysts and modelers, though, what we want to do is reveal general information about the data set without exposing specific personal information. So this is the idea behind private data analysis as a field, and I think it goes hand in hand with what we already tried to do in machine learning. So in machine learning, the goal, of course, is to train a model that generalizes well to unseen data, and to do that, we need to ensure it's not overfitting to specific individual data points. Okay, but this sounds very similar to what we want to do in private data analysis. We want to extract high-level information or statistics, and we want to avoid exposing low-level personal information. So this new paradigm of private data analysis gets us thinking about privacy as something that's not binary, but something that is consumed the more and more we extract information from our data. The question we need to answer then is, how can we extract the most useful information while exposing or consuming the least amount of privacy? I'm having trouble flicking forward. Maybe at the back you can go forward when I say so. Great. So this brings us to the topic of privacy-enhancing technologies, which are a set of tools that allow us to minimize the risk to individuals that their personally identifiable information will be exposed, while at the same time maximizing the utility of our data sets for the analysis that we're trying to do. I've listed here 4 example privacy-enhancing technologies that are actively being researched in the local community, and I'll talk about 2 of them today, which have interesting interactions with fairness. So the first is federated learning. You might already know that federated learning is a distributed machine learning approach where instead of pooling data together like we would normally do and training a single model, we leave the data where it is, at the place where it was generated or collected. And instead we move the computation to the data. So in federated learning, models are trained at the device, like a mobile phone, or at the institution where the data was generated. And in some sense, this is more private than the alternative, because raw data never leaves the device where it was generated or the institution where it was collected. If you're not familiar with federated learning, I think it's most easy to understand it through a simple example. This is the most prototypical algorithm that's used in this space. It's called FedAVG. So it's a simple 4-step procedure. At the very beginning, we have a central server who initializes the model in some way. And that server communicates copies of the model to all the participating clients, we'll call them. Step 2, each of the clients takes the model they've received and they train it on their local data set. So this extracts some information from their local data. And in step 3, this is the only time when information leaves the clients, they send their updated models back to the server. And to be clear, they're not sending anything involving their raw data, just the models or the updated models. And finally, in step 4, when the central server has all of the updated local models, the server will average them together or aggregate them together in some way to get a updated central model, which is hopefully stronger because it's had access to a wider array of data, a more diverse set of data spread across all these clients. And then this process can be repeated as much as required. So now let's consider fairness in this context, starting with the server. So let's say the server is a noble entity and they want to train a model which is fair across all of their clients. We think back to the examples of how we could improve fairness in machine learning that I mentioned before. Could the server try to request updates from minority clients more often to take into account we have less of their data? Or could the server, when it's averaging things together, weight some of the clients' updates more heavily? Well, the answer is a clear no, not at all. Because the server doesn't have any access to raw data. In particular, it will not have access to the group labels. So how could it know which updates or which clients it's supposed to oversample? It can't. The server's only role is to aggregate models together and communicate models back and forth. It never does evaluation because that's the whole point of this privacy approach. The server doesn't have any raw data. So if the server can't influence the fairness of the model that's being trained, it must be the clients. Let's look at what the clients can do. Could the clients rebalance their local data in some way? Could they change how they're training models to weight data from minorities more heavily? It's more subtle this time, but the answer is still no. Each client only knows its local distribution of data. Again, by the privacy constraints of this framework, they don't know anything about the distribution of data at other clients. So what a local client sees as a minority might actually be a global majority, or vice versa. So any decisions that a client makes for rebalancing its own data set or changing its training mechanism will be based only on its local information, which might not accord with the global information. In other words, if the client chooses to change its process at all, it might do more harm than good. There's no real way to know. So this brings us to, I think, the main problem of federated learning when it comes to unfairness, which is that you can't identify when unfairness is occurring. The clients can't do it and the server can't do it either. As an extreme example, well, let's say that the clients try to evaluate fairness locally. The problem here is that local fairness does not translate into global fairness. And the extreme example which I can give to you is, imagine we have a federated learning system with mobile phones as the devices collecting some information in an app. Each mobile phone probably belongs to a single user, and that single user probably has a single gender, whatever it is. And so how can they possibly evaluate fairness across this gender label or age, whatever it happens to be? Each client can look at their data set and say, yeah, I get a certain level of performance on my data set, but that doesn't tell us anything about the performance on a different group that we care about. So local fairness does not allow us to imply anything about global fairness. And building on this idea, as we train models in federated learning, it's very possible that the central model that's been trained does well on a majority of clients, but there's a few clients out there that it really struggles on. It does very poorly. In fact, it can do so poorly that those given clients would be better off to just train a model on their local data and forget about the collaboration altogether. Once again, the problem is the server will not realize when this is happening because the server doesn't evaluate anything due to the privacy constraints of the setting. So I do think there are some solutions in this space that can be used to improve the fairness of federated learning. One is personalized FL. In personalized FL, the clients don't just use the central model they've been given, but they personalize it in some way before use. They might update it based on their local data. They could, for example, train a local model and compare the performance to make sure that there's actually improvement. And in this way, we can at least ensure that no clients are worse off by collaborating than they would be if they just kept to themselves. Another interesting approach is decentralized federated learning. As it sounds, we get rid of the central server altogether, and instead each client has to maintain their own model, and they collaborate with each other in a peer-to-peer manner. So this goes a long way to putting the power back in the hands of the users and control over what happens with their data. In particular, clients are able to select other peers that they want to collaborate with based on similarity between data distributions and the usefulness of the updates they're getting. So all this talk about federated learning, I hope makes us think about the question, is sharing model updates more private than sharing raw data? And whatever you think the answer is to that question, the key point here is that we're not thinking of privacy as a binary notion anymore. It's a resource. It's something that gets used up as we reveal more and more information. And differential privacy is a mathematical framework that allows us to quantify how private some analysis is. And because it's rigorous, it allows us to provide meaningful guarantees to users about how much privacy they'll be afforded. Differential privacy is a bit more technical than the last subject, but I'll try to put it in simple terms. As it turns out, randomness is a very useful way to achieve privacy. Think about a data set that has some outliers in it. Those outliers stick out like a sore thumb, and they're at a higher risk of having their privacy exposed. By adding some randomness to the data in some way, you can kind of smooth out the data and hide those outliers a bit more. Differential privacy is a notion that works with randomized queries that give us some answers about a data set, but not deterministically. So if you've ever used an Excel spreadsheet or SQL database and you've queried it, you know you always get back the same answer for a given query. It's deterministic. There is a true answer. That's not the way that differential privacy operates. Instead of giving us a single true deterministic answer, a differentially private query or a randomized query will have many possible results, including the true answer. And each result will have some probability of being returned when we ask the query. So the intuitive idea here is that what our goal is to have that every possible result from the query has a likelihood that's more or less unchanged when we add a new data point to the data set. This might not be obvious at first, but think about what happens in the opposite case. We start with a data set and a query that has some distribution of results. If I were to add one more data point to that data set and rerun the query, if I was to get a completely different distribution of results, that means that the query is picking up a lot on the information of one single data point, which is not private at all. We want the addition of one data point to have very little influence on what we're doing so that we're not learning information about individual data points. So to be a bit more technical, in differential privacy, we say that a query is differentially private if the results are almost indistinguishable when one data point is added to our data set. The problem here is that differential privacy makes unfairness worse. The whole objective that I'm trying to describe is that differential privacy should obscure low-level information about individual data points. And we do this through randomness. But randomness naturally affects outliers and minority groups more because these groups have smaller populations, and so they're more affected by noise compared to larger populations. So as it turns out, if you have a model which has some unfairness in it and you add differential privacy, that unfairness is amplified This plot shows an example of a model trained without DP, and it has a slight difference in accuracy for 2 skin shades. And after differential privacy is added, the difference between accuracy is much larger. There's much more unfairness. And this is a typical case. So I'll explain what we can do with differential privacy to try to correct its unfairness in a specific example. This is the most commonly used single approach to differential privacy, and it's used to train machine learning models like neural networks. It's called DP-SGD. The normal thing we would do is stochastic gradient descent, SGD, where we compute gradients according to some loss function and apply that as an update to our model. The idea of DP-SGD is that we're going to try to construct a privacy barrier between the data and the model that's being trained so that we have some guarantees of how much information will be leaked from the model, hopefully a small amount. So DP-SGD changes the ordinary SGD approach in 2 ways. It takes the gradients that we would normally use to update the model, and we first clip them. If they're too large, we bring them down to size. And this limits the amount of influence that any one data point can have on the model. And the second thing we do is add noise, because usually the SGD gradients are deterministic, so we need to randomize them for DP. You can see on the bottom here a figure of what that looks like. We have gradients that are computed for individual data samples. The largest ones are clipped down to size, and then they're averaged together, and we add noise to it for randomization. So let's see how this impacts the fairness of the models that are trained. To begin with, we know that a model will need more exposure to underrepresented or complex groups in order to learn them properly. That implies that data points coming from these groups will have larger gradients throughout training because they haven't been learned as well so far. But since they have larger gradients, that means they're more likely to be clipped down to size, which was one of our requirements. But clipping itself decreases the influence that these data points have. So we've entered a negative feedback loop of unfairness, where the data we need to pay most attention to has its influence decreased at every iteration. This can be solved to a large extent by changing the common algorithm of DP-SGD in one simple way, which is instead of only clipping the largest gradients, we scale down all data, all gradients by the same amount, by the same factor, let's say. In fact, this approach has been studied in some recent research, and in many cases, it can entirely remove disparate impact in our models that's generated by the effect of DP-SGD. So we've come a long way in a short amount of time, starting from some basics of privacy and fairness, getting to very technical topics in differential privacy. But I hope that you can take away the point that if we're not careful, privacy-enhancing technologies can actually have very negative adverse effects on the fairness of models that are being trained. In the example of federated learning, the privacy requirements of that approach prevent the central server from identifying when unfairness is occurring. And so if you're not explicitly looking for it, you might be unknowingly training very unfair models. And in differential privacy, which is based on randomness, we found that this randomization is more likely to obscure the data points that we needed to pay attention to the most. So this negative feedback loop of unfairness occurs. So I hope that your takeaway from this talk is that we should not just be thinking about privacy and fairness on their own in our institutions and our day-to-day jobs. We really need to consider the intersectionality between these two concepts, especially if we're going to be deploying machine learning in highly regulated industries like healthcare and finance. So thanks for your attention. I'm happy to answer questions from the audience. Are we using the mic back there?
Yes.
Okay.
Thank you. Okay, my question to you is this. There is a technique called homomorphic encryption,
Yes.
wherein data sets are basically encrypted and computations are run on the encrypted data set, and that is used to train the model. why is that not an alternative for maintaining both privacy and fairness in training a data set?
It is an alternative, and it's a very good alternative. So I had one slide introducing privacy-enhancing technologies where I listed 4: federated learning, differential privacy, which I talked about. The other 2 are homomorphic encryption, as you say, and secure multi-party computation. These are both cryptographic approaches that do add privacy in a different way, and they're very effective at what they do. And I would say they generally have very little consequences when it comes to unfairness, which is why I didn't feel the need to talk about them. But yeah, I think those approaches are good alternatives, but they make different assumptions and they're useful in different settings.
Thank you.
I have a question regarding the DPSGD scaling. If you scale them all the same way with the clipping, so aren't you not introducing differential privacy anymore because they're all scaled the same way?
Yeah, we're getting into more technical ideas. For the sake of this talk, I tried to keep it high level. I think what you're getting at is DP requires a finite sensitivity of the randomized query that we're building. So you're absolutely right. Just scaling down gradients does not introduce a finite sensitivity. So the technique that I listed, do feel free to look up the paper that was there, but it incorporates both scaling and clipping on the largest sets of gradients. So it does have a mechanism to give a finite sensitivity. So very astute observation. We have experts in the audience.
Hello. Yeah. So it was a great presentation, and my question is regarding federated learning
Yeah.
and how it might impact the power consumption of devices. Is that aspect something that you have considered?
Sorry, could you repeat what aspect you're asking about?
The power consumption of devices, like
Oh.
when you have, yeah.
So the power consumption. Was there a particular question you had about power consumption?
Not really not a particular question, but just the case that like if you have like multiple ML models running on each devices, like for instance, like your mobile phone,
Yep.
then the power consumption of such the application is going to jump high, and then your battery is going to die off sooner.
Yeah.
So my background is from electrical engineering, so maybe I just wanted to know if that aspect is being monitored or being researched.
Yeah, okay, it's absolutely being researched. Yeah, it's a very major concern when deploying these things. There's generally 2 regimes that we think about federated learning. It was initially developed and invented for communication between mobile phones. So your app collects some data. You don't want that data to leave your device. So instead, the model's trained and the model gets sent back to the server. In that case, power consumption is a very big deal. And so usually when these have been deployed in the real world, the federated learning, the training only happens when a device is plugged in and connected to a Wi-Fi network. So it's not using your mobile data, right? That would be terrible. The other regime is where we think of large institutions collaborating together, which have a lot of resources. So it's much less of a concern there.
Hi there. One question at the backside. Thank you so much, Jesse, for a great presentation. I was wondering, there's private information, and then there are other features that could be used to infer private information that can almost act as a proxy, and that often happens both in insurance as well as in healthcare. Among the 4 techniques that you had mentioned in that slide, do you feel is there one technique that outshines others in being able to take care of that aspect, or not really?
So let me stick with the 2 main ones that I introduced because people in the room will be familiar with it. So federated learning, the idea is we only share model updates. The problem with that, which I didn't get into, is that model updates can still contain a wide array of information inside them. It's well known in machine learning that neural networks have the capacity to memorize their training data. So it's also sometimes possible to extract training data from a trained model. So if you're giving someone a trained model, there's a big risk that they can extract your training data from it. So in that sense, I don't think it goes very far to protecting personal information or proxies to it. I think the more promising approach is differential privacy. So your point is about even if we redact some particular field from our data, there might be proxies for it in the rest of our data. Well, differential privacy, I don't think is largely concerned with this because it gives us mathematically rigorous guarantees about how much information can be leaked. It gives you an upper bound on the amount of information that can come out. So it's not like federated learning where we don't really know what's being transferred when we send our models. DP gives us rigorous bounds. So I think both of these techniques are well outside the framework of anonymization, removing personally identifiable information. It's a completely new paradigm that we're thinking about here.
Okay. The concept that you said, privacy enhancing technologies can have adverse impacts on fairness. If we consider like those sections of the database that are related to the privacy matters, if we choose to hash them and then use a kind of hashing solution that wherever we need those privacy matters, we unhash those sections to use them as like flag them or by like labeling or group them in a sort of manner that okay, these are men or female or if they have any specific ideas or any specific selections, so we can have group-wise them, and then by hashing those solutions, if we need any specific kind of information, then we would unhash them. How would this kind of solution can it be helpful for the solution for the condition that we have, or?
So as it relates to fairness, what you describe, I don't think it has many impacts on fairness. It sounds more similar to the ideas of homomorphic encryption or secure multi-party computation, which generally don't interact with unfairness. The conclusions of my talk is that some privacy-enhancing technologies can have adverse impacts. And if you're not aware of that, if you're not looking for it, you probably won't notice. But if you want to talk more offline, I'd be happy to. I think we probably need to move to the next session. Okay, so thank you again for your attention, everyone.